Okay, the last talk of the day is by Prahladh Harsha. So I think we are convinced now, all of us, that coding theory is important, right? So we should pay attention to this talk. So Prahladh talks about this fast algorithm for list decoding. So we really need 10 time algorithm for list decoding.
Yeah, there's no don't need to give a formal introduction to coding theory. So
this is the title I wanted to talk about, but given that I felt I should not give it a coding theory angle, so I actually said this is the title I should actually talk about, so that not to sell it as a coding theory talk, but post Rohit's talk, I think I can go back to the So this is based on sequence. This talk is based on joint work with Mrinal, and who's here, Ashutosh Shankar, who's a grad student, mine at TIFR, and Rohan Goyal, who was visiting TIFR and is currently a grad student at MIT. So when Srikanth asked me to give this talk based on these works, what I thought, instead of actually just talking about our works, which were trying to get nearly linear implementations of some list decoding algorithm, what I instead do is an overview of algorithmic list decoding of polynomial-based codes since Madhu's seminal algorithm from the mid-90s, and what have been the work that goes towards getting nearly linear time implementations of these algorithms since then. So give an overview of sort of work. So let's start off with our most favorite code, the Reed-Solomon code. So the Reed-Solomon code is based on this degree mantra that two distinct polynomials of degree are less than k evaluated on any set of n distinct points cannot agree on more than cannot agree on k or more points. And this immediately tells us that we can construct this code, which is just the evaluations of univariate polynomials of degree less than k on some set yes of n points. And the degree mantra immediately tells us that the distance of this code is n minus k plus 1, and hence its unique decoding radius. As long as the number of corruptions is less than half the distance, one can at least combinatorially decode and find the closest code word. So we can account for we can easily accommodate so many errors, so many corruptions in the code. The rate is yeah. So what's the problem we'll be dealing with? We'll be dealing with, now suppose there are errors in the Reed-Solomon code word has been corrupted. We would like to decode from the corruption. So let's take the problem more familiar language, in the language of noisy polynomial interpolation. So we're given a received word, which is a set of n pairs of points, and we want to find every polynomial for which satisfies that p of alpha I is equal to beta I for as many points as possible. Question is what is the as many we want to accommodate? We'll try to understand this closely. So what is many? If many is everything, then this is just interpolation. This is just the interpolation problem, noiseless interpolation, and we know how to do this. We also know how to do this extremely efficiently. Question is, if many was n plus k by 2, this is exactly what's dictated by the unique decoding radius, then we know at least combinatorially you can do this. So you can ask, can we get algorithmic versions of this? And there's been work of it. Now you could we will soon see, I'll soon list the algorithmic results in this context. We could ask, can we even do more? Can we even do, with even lesser agreement, can you find out the list of all polynomials that agree with? N plus k by 2, there is 1. Once you want even lesser agreement than n plus k by 2, you can no longer guarantee a unique code word, but there's possibly a small list of code words that you can guarantee. And in fact, one can show that if you go up to the agreement not from n plus k by 2, that which is the arithmetic mean of n and k, to even a smaller number, square root of nk, which is the geometric mean, it's even lesser agreement this, you still can guarantee that the number of code words in this ball is actually polynomially many. So you can expect to do this, and this radius is called the Johnson radius in coding theory. You could ask even further, you can be even greedier and say, even with lesser agreement can you do? How less can one expect to go? Or you at least need to give k symbols, because that's the amount of information you need to get even one polynomial. Can we do it something better than that? And this is, by the way, this is still open. And several of the results that Rohit mentioned we're trying to understand what is the capacity of Reed-Solomon codes, the list decoding Reed-Solomon codes. Yeah, so I think I don't have to do this. This is just everything that I had said in the previous slide for polynomials. This is stating it more in the language of codes for general codes. Okay. Kept this slide, and let's go back to the list decoding problem, which is we had. What were the? I just want to mention one more problem. Given that this was the list decoding problem, we'll be trying to understand for the rest of the talk. This is for Reed-Solomon code. Later on, we'll modify it to some other variants of Reed-Solomon code, Reed-Solomon codes and various friends of Reed-Solomon codes. We'll also be interested in a closely related problem in which instead of giving for every alpha, instead of just giving one beta 1, we actually give a list of betas and ask. So basically, it's what's called the list recovery problem. So we give not B1 is not just one code word, it's a list of potential values, and we want to find all polynomials so that for several alpha i's, we have that the P of alpha lies in the set Bi. This is called the list recovery problem, and almost all the algorithms that we'll see stock will actually also work for list recovery, will naturally work for list recovery. So what's known, what are the algorithmic results that we know for the decoding problem? Almost very soon after the discovery of the Reed-Solomon code, the code itself, we had a sequence of algorithms for unique decoding the Reed-Solomon codes. We had Peterson's algorithms, the Berlekamp-Macy algorithm, Berlekamp-Welch, and in fact, very soon after Berlekamp-Macy algorithm, almost immediately after, we had nearly linear time implementations of these algorithms also. The original algorithms were polynomial time, and there are subsequently nearly linear time implementations of each of these algorithms. What about in the list decoding context? So there's this seminal work of Madhu followed by Venkat and Madhu's work, which showed that you can list decode Reed-Solomon codes all the way up to the Johnson radius, up to square root nk. And if I ask a question more, in fact, the sequence of works that Rohit had mentioned, we're trying to understand, can we improve the results of Guruswami-Sudan and list decode even from a smaller agreement? What we do know, in fact, the last result, Brackensik, Gopi and Makam's work shows that in fact you can, if this choice set of evaluations, if you choose it for a random set of evaluations, then in fact you can go all the way up to capacity. Unfortunately, this is it's only true, we only know how to show it for non-explicit. The question for explicit sets for which we can do this is still open. This is a wide open problem. That's not what I'll be focusing on this talk. We'll be focusing on algorithmic results for which we know polynomial time algorithms, and we'll ask, given that we know that they are polynomial time algorithms, can we get nearly linear time implementations of these algorithms? Okay. So there's two directions. After Guruswami-Sudan's algorithm, we'll be wondering how to improve the list decoding capacity. We have not yet been able to do this for Reed-Solomon codes. We instead ask if there are other codes for which we can actually improve, go beyond the Johnson radius. And it was discovered, in fact, once again, I think Rohit gave a far more exhaustive, he should have retained that exhaustive survey of list decoding. Guruswami-Rudra, following work by Pavareshwari, Guruswami-Rudra showed that the folded Reed-Solomon code actually achieves the list decoding capacity. In this talk, I will not focus on folded Reed-Solomon codes, but a close variant of it called the univariate multiplicity code. So, which is I find it more nicer to describe it. So it's also based on the degree mantra that we studied. So the same is also true of folded Reed-Solomon codes. It says that the two distinct polynomials have a set of size n cannot agree on more than k points. By the way, this mantra is also true if you include multiplicities at a point. You have to count not just a zero, but the number of multiplicities. In particular, if you modify the code in which by not just giving the evaluation, but you also give the derivatives at the point. So if you give s derivatives, then you can have, and then you can ask how many agreements can you have? Then you can have only k minus 1 over s agreements. Because if you have more agreements, if are more than k minus 1 over s points, if the points as well as the derivatives, evaluation as well as derivatives agree, then you are going to have, then the 2 points are going, then the two polynomials are going to be identical polynomials. So this lets us define what we call the univariate multiplicity code, which is identical to the Reed-Solomon code, except that at each point you not just give the evaluation, but you also give a derivatives, and you give up to some parameter. There's a folding parameter called S. You give up to the S derivative over there. And that's the distance, rate, that. And you can ask exactly the same question, the list decoding question over here, which is exactly in which the algebraic word is the noisy Hermite interpolation. You are given a list of such ones, alpha 1, and purported evaluations and derivatives at various points. You want to find every polynomial p for which for most alpha i's, p alpha I is beta I, as well as all the higher derivatives also early. You want to find this, and this is noisy Hermite interpolation, the algebraic word, or in the coding theory language, this is just list decoding univariate multiplicity codes. And works of firstly Kopparty and Guruswami and Wang show that these codes are actually list decodable all the way up to capacity. This and their counterpart for Reed-Solomon codes. For the purpose of this talk, I'll be focusing only on univariate multiplicity codes, but everything that I say also extends to FRS codes. Okay, so little did I know, once again Rohit will give, this is also going to be an exhaustive history of list decoding. So we begin with Madhu's algorithm from 96, followed by Guruswami-Sudan's algorithm of Reed-Solomon codes. Then we had Parvaresh-Vardi. These are all I'm doing putting up a subset of Rohit's list in the context of algorithmic list decoding. We had Guruswami-Rudra, which gave the first capacity achieving algorithmic list decodable codes. Then there was a work of Kopparty and Guruswami-Wang who proved the same result for multiplicity codes, is what I mentioned earlier. And this was state of affairs. All these results show you that you have polynomial time algorithms for list decoding. We could now ask, do we have nearly linear time algorithms? In fact, very soon after Venkat and Madhu's work, Misha Alekhnovich gave a nearly linear time version of the Guruswami-Sudan algorithm. And in fact, we will spend a lot of time trying to understand Misha's implementation of the Guruswami-Sudan algorithm later. Now we could ask, given that we have nearly linear time implementation of the Guruswami-Sudan algorithm, do we have nearly linear time implementations of the Kopparty and the Guruswami-Wang or the Guruswami-Rudra algorithms? And here, firstly you should ask, can we even expect such a thing? Because out there we had the Johnson radius which said the list size was constant. Therefore, one could expect nearly linear time implementations. Here, there was no bound on the list size. The list size in principle could be polynomially large, and then there's no way we can expect nearly linear time implementations. So, this point we can't, please, just with the knowledge over here, the only bound on the list size was the running time of the algorithm. We didn't have any constant size, any further bound on the list size after the works of Kopparty and Guruswami-Wang. But this was rectified by work of Swastik, Noga, Shubhangi and Mary, who showed that even though these algorithms took polynomial time, you can actually show that the list sizes are constant in 1 over epsilon. It has no end dependence. The dependence on epsilon was bad here, it was exponential dependence, but it was a fixed constant, so the constant depending on epsilon. So once we have this particular result, you can expect to get nearly linear time algorithm because the list size is now constant, so you can expect an algorithm which just runs in nearly linear time. In fact, that was the first result which we showed. We joint work with Rohan on this one. We showed that the Guruswami-Wang algorithm can be implemented actually in nearly linear time. And since then, there's been a lot of work. For example, as Rohit mentioned, Shashank and Chen and Zhang showed that this list size which Kopparty et al. Had showed can actually, you can further get it down and get to the optimal list size. And in what sense is it optimal? It matches the generalized singleton bound of Shango and Tama. So in that sense, it was optimal. It actually showed that the list size for folded Reed-Solomon and univariate multiplicity codes were optimal. We extended this to even the list recovery algorithm, and more recently, Ashwin Kumar Habib and Srivastava showed not just is the list size optimal, that is, you can actually give an algorithmic version to get the list size to be an algorithm which will get the right list size. By the way, I must mention the Kopparty-Ronsevi was also an algorithmic result. They showed constant size, and they gave a pruning algorithm which will have an exponential dependence on epsilon. This was an algorithm which had only a polynomial dependence on epsilon and gave you the right list. So what I will do in the rest of the talk is survey these three results, the three results which talk about linear time algorithms. Alekhnovich's result and our results tell you what are the ingredients that go into these results in order to get nearly linear time implementations of the other list decoding algorithms. Any questions? Point. So these are the results which I will be sort of showing you. These are informally stated. Basically, for each Solomon, you'll see Alekhnovich result, which says that there is a nearly linear time implementation that of the Guruswami-Sudan algorithm, and for univariate multiplicity, we'll show a nearly linear time implementation of noisy Hermite interpolation. Similar results hold good for even list recovery, except that this poly 1 over epsilon will be actually x 1 over epsilon, and it is known that an exponential dependence on epsilon is needed. Chen and Zhang actually gave examples in which for the list recovery problem, the list sizes can be exponential in epsilon. So it's needed over here. So out here, the dependence on epsilon will change to exponential 1 over epsilon for the list recovery problem. Okay? Questions? Otherwise, we'll sort of spend time. We'll sort of go over the main ingredients. We'll look at the prototype algorithms behind these are list decoding algorithms, and then see what components of them were not running in nearly linear time and how can we make them linear. How am I doing with respect to time? And
10 minutes, I think.
yeah. So let's start with the algorithm that started this whole thing, Madhu's algorithm for Reed-Solomon list decoding. So you're given, that's the problem we have. And all of these algorithms have these two steps, in which the first step, you're going to find an algebraic explanation for the entire data. The data, notice that some of the points are valid points, some of the points are noisy points. And what do I mean by an algebraic explanation? We'll find a non-zero, a bivariate. Notice we are interested in univariate polynomial, a bivariate polynomial q of xy, such that every point, every pair alpha is actually a root of this, is a zero of the bivariate polynomial, and the degrees of the x degree and the y degree of the bivariate polynomial is not too large. And why can you find such a polynomial? You just do dimension counting. You write a set of linear system in the variables, in the coefficients of the polynomial, show that there are more number of variables than constraints, and hence they exist a non-zero polynomial. So this step is just solving a linear system. And now notice that if there exists a polynomial R of x that agrees with the received word on many points, then actually that polynomial will, from this you will be able to observe that actually this polynomial is actually a factor, is a root of the bivariate polynomial. So in particular, this tells you the next step is an obvious step. You factorize q of xy and output all factors of the form y minus rx. This will contain the entire list of, this list will contain all the polynomials that we are in search of. So this is Sudan's algorithm, and the only difference between the Sudan's algorithms and the subsequent algorithm, one is the previous step we had talked about just finding a q that vanishes on all the points. Guruswami-Sudan improvement was you not just find a q that vanishes, but also vanishes up to a higher order of multiplicity. And this modification let them decode all the way up to the Johnson radius. Given this, let's ask, both these steps are polynomial time. The first is solving a linear system, the second is bivariate polynomial factorization. They're both efficient. The second one is a randomized algorithm, but neither of the steps, as stated, run in nearly linear time. So let's ask us, how can we make it in linear time? And actually the bottleneck is not this. There are two steps, as I mentioned, the interpolation step and the factorization step. The bottleneck is in the interpolation. You have to solve a system of equations, it's a polynomial system of equations. It's not clear how to do it in nearly linear time. The second step seems as if you're doing to improve factorization, but it's not factorization. You're only interested in root finding. Factorization, we still don't know how to get nearly linear time implementations of factorization, but root finding, we know how to do it, and so the second step, in fact, even in the Guruswami-Sudan algorithm, is actually nearly linear time. It's the first step that was this one, and this is where Alekhnovich's improvement comes. So is the issue here clear? We will now go into how to make the first step nearly linear. So let's recall. The first step is find some q of small degree which vanishes on some set of points with high multiplicity. This is the step. It's solving a linear system. If this linear system had nice properties, for example, it was sparse or something, one could expect it to have a faster solution. But it's not necessarily sparse. So Alekhnovich takes a very different approach. What he notices is, let's look at the bivariate polynomial as a vector with entries from f of x. In particular, the nth coordinate is the coefficient of y power n. So you think of this as a vector whose entries come from the polynomial ring f of x. It's not hard to see that the set of polynomials that vanish, that we are in search of, is actually a lattice. More formally, an fx module. That is, you multiply this vector by elements from f of x, it will remain as one of the polynomials that we have. So in principle, what we are trying to do is we are searching in this module or this lattice for a vector of as low degree size as possible. We are in particular, we are running the shortest vector problem on this particular lattice. So Alekhnovich's observation was this. So we want a small by weighted degree polynomial in this lattice. That's what we want. And nice thing about this, notice this lattice. This lattice, you can give us a nice base. Firstly, you have to find a basis for this lattice. Notice is the dimension of this lattice is exactly the y degree, which is, if you notice in all the algorithms we talked about, is a constant. So it's a constant dimensional lattice. The entries of it are potentially large. The entries are the polynomials in f of x. These possibly have degree order n. So it's a lattice. It's a constant dimensional lattice in which the entries are order n degree polynomials, and you want to find some shortest vector in this. This happens to be a problem which we can do in polynomial time, in fact linear time, in the size of the entry. It's polynomial in the dimension. I didn't care about the dimension. The dimension is constant, but the entries are linear. You can do this, and in particular, you can use a polynomial lattice. This is different from the integer case where the corresponding integer lattice problems are hard. This is in the polynomial case, these shortest vector lattice problems are actually you can do them in polynomial time. In fact, they run in poly time in the dimension and nearly linear time in the size of the entries that go into the vector. The size of the entries is order n. Therefore, this is an algorithm that runs in order n poly. So this alternate view of looking at this of the set of polynomials that satisfies this as a lattice let Alekhnovich actually give a nearly linear time implementation. To say a few more words out here. So firstly, how does in the original in Sudan and Guruswami-Sudan's version of the algorithm, we were able to show that there was a queue of the right thing by just doing this dimension counting. This one. Here you will be constructing some basis for the lattice, and you can find out the shortest vector in that lattice. How do you know that the shortest vector has the degree guarantees that you want to? So there are two ways to do it. The way Alekhnovich did it is he came up with a basis and then showed that this lattice is identical to the lattice constructed by Sudan or Guruswami-Sudan. And the way he showed it is actually came up with a Grabner basis for the two lattices and showed that they are identical. You can take what we observe is actually you can do a simpler thing. This is because it's a lattice, you can actually use Minkowski's theorem to show that there is a vector of there's a short vector in it, and the Minkowski theorem exactly happens to match to the dimension counting algorithm. So you can this is in the analysis, it's not needed for the analysis. Alekhnovich used Grobner basis of the lattices to show that this lattice is identical. What you can instead show is just use Minkowski theorem and show that there's a short vector in the lattice. Yeah, with this was that's basically all of it that went into Alekhnovich making the Guruswami-Sudan algorithm run in linear time. Any questions? So we'll now go to extending the same idea to multiplicities. Okay? You want to know the multiplicities, and let's look at the Guruswami-Wang algorithm in this setting. There are two algorithms for this case. This is called First-X algorithm and the Guruswami-Wang. We will be able to get linear implementation of Guruswami-Wang. We don't yet know how to do a linear implementation of Kopparty's algorithm. So it has two steps as before. There's an interpolation step in which you find a polynomial, instead of a bivariate, now you find some m plus 1 variate that explains the data, input data completely. And these are input data completely, and then once again this can be done by solving a system of linear equations. This is how Guruswami-Wang did it, and then you show that every polynomial that is close to the received word will satisfy this differential equation, and so the second step will be just solve this differential equation to get all the points in Rx. So once again, this version of Guruswami-Wang is efficient and decodes up to capacity, but it's not nearly linear time. How do we make it linear time? Back again, we look at both the steps. And this step, we exactly follow Alekhnovich's idea. We view this solution of linear system as a lattice and try to solve this lattice and use Minkowski theorem to find the shortest vector in the lattice. And that does. This is exactly identical to Alekhnovich. The only non-trivial part of it was trying to find a basis for the lattice. For list decoding, the basis is more or less there's a very natural basis one can construct. That's a basis for the lattice, and then find the shortest vector. For list recovery, we had to do more work. Even coming up with the basis actually required more work. These are unknown polynomials. You have to solve some. But we can show that we can obtain all of them in nearly linear time. So this was for list decoding and list recovery. So that's the first step of the algorithm. But the second step in the case of Guruswami-Sudan was just root finding, but here you are left with solving differential equations. So what we now need to ask is, can these differential equations, when you're given a differential equation of this form, in particular you're given the polynomials a0x, a1x, a2x, amx, you're given these polynomials, you want to find all polynomials r of x that satisfy this differential equation. Question is, can you find it in nearly linear time? First thing to notice is, if this set of solutions to this forms an affine subspace of dimension m. That is, if two things are this one, their affine combination will also be a solution to this. So it's sufficient for us to just find a basis for this affine space, not necessarily find every solution. So let's try to see how to do it. Let's even ask the simplest version of this problem, in which m is 1. So a0x plus a1x rx. How do you find this in nearly linear time? This is just division. This is just this polynomial division. The obvious thing is division, but we want to do it in linear time. We do know off-the-shelf algorithms to do division in linear time. Let's actually stare at this algorithm a little more and see if we can modify that algorithm to even solve the other algorithm. So what's the division algorithm we have? That's the problem we have. We want to find r of x, so that a0x. This one, the standard thing, the FFT is the sort of trick that Josh was talking about. We're going to break the problem into smaller problems of the same type, use divide and conquer to solve it. So you write r of x as the, by the way, I don't have to do this for this audience. I can just flash these slides. So this is a standard, you do breaking up two parts, and you break up the single problem into two parts. Say, we want to find a solution r for this problem. We've broken into two parts in which the degree has gone down by half. This one is two smaller problems of the same type, you recurse and you will find it. So this is, and ask us, we would like to exactly do the same thing for the higher order differential equation. We would like to do exactly this one. How does one manage it? The first problem we'll raise is, the solution is no longer unique. Division, there was just one answer, therefore divide and conquer will let you do it. If you do the natural thing over there, if you want to branch, there could be multiple solutions, and in divide and conquer, if there are multiple solutions, it's just going to blow up. If you have, each time there are even two solutions, these number of solutions will blow up and your list size will become exponentially large. Because if you carefully stare at it, you'll notice that, firstly, as I mentioned before, we don't need to get all the solutions, we only need to get a basis of the solutions. Notice that if for each of the bases, so what we observe that, if you observe this carefully as the differential equation, for each of the basis vector, instead of working with this differential equation, you show there's another differential equation such that if for that basis, if you fix initial this ones, then onwards the solution is only unique. And the solution is exactly what I said. What happened in long division, fast implemented division, the exact same steps will happen here, and that's exactly how we do it. Here, a version of divide and conquer works here, and we get this. This is how we solve differential equations of higher degree. Yeah. So just summarizing, so these were sort of using this lattice-based approach of Alekhnovich and the fast differential equations. We have nearly linear time implementations of this decoding both Reed-Solomon codes, univariate multiplicity codes, and the same thing works also for folded Reed-Solomon codes. Okay. All I have to say is just the question is, can we extend these to multivariate polynomials? This solving differential equations, this decoding problem. Don't know how to do this. The other thing is, I mentioned earlier, we said there were two list decoding algorithms for univariate multiplicity codes. There was Guruswami-Wang's algorithm and Kopparty's algorithm. Guruswami-Wang's algorithm was nice that the underlying differential equation was linear, and we used that property crucially, whereas Kopparty's algorithm was non-linear, and I don't know how to solve this for non-linear. It will be interesting for if we can get fast implementations even for non-linear or ordinary differential equations. And of course, more generally, the problem is trying to understand what's this decoding limits of Reed-Solomon. Start with this. Thanks.
Can you say a little bit about like what is the intuition for that proxy? Like, is there any intuitive way to see that proxy that you construct?
No, so the thing you notice is once you realize it's not a proxy, we first notice that it's an m-dimensional system. So, and it's easy to check that so the question is there a nice basis for the m-dimensional system? Notice that if you fix the first lower order m coefficients of the polynomial that you're searching for, there's all the uncertainty if you stare at the differential, the uncertainty comes only in the first m different. This one. Once you fix them, then onwards the differential equation, the branching factor, you can actually show that it is unique. So you fix the first m and then go ahead with it. That's all.
So in the list recovery setting, is it known that the set of code words that you're looking for is still in a low dimensional space?
The Guruswami-Wang's algorithm, everything works. Everything that I said works for both list decoding and list recovery.
So which means that, I mean,
what you will get is I will give you an order 1 over epsilon dimensional space in which the entire list resides. Question is, from there, how do you get to the actual code words?
But until that point, is it still like poly in 1 over epsilon?
Until that time, it's poly in 1 over epsilon. From there to actually come to the exact list, you have to find. So right now, we have this. So the algorithm I described only gives you a basis for the solution. The actual solutions reside somewhere in this affine space. So you have to do a pruning algorithm. The Kopparty et al. Algorithm does a pruning which gets exponential 1 over epsilon. The Ashwin Kumar Habib Srivastava does it for list decoding, and we know that for list recovery you don't have such a counterpart.
So for the list recovery bound, you said this exponential in 1 over epsilon thing.
Mm-hmm.
Is this for both like FRS codes and multiplicity codes? Or?
Yes, I think you can look at the Chinese. I think they write it for FRS, but I think an almost identical counterexample holds good for multiplicity codes.
So you just come up with some field elements?
Yes, so you come up with a received word, a received word in which for every alpha you have a bucket of elements, and this will be close to 2 exponentially many code words in 1 over epsilon.
Okay,
The list will be linear, but it will be exponentially in 1 over epsilon.
More question? Okay, if not, then